So we need a force given over a certain distance. Now, today what we're going to think about, and I've kind of alluded to this already, is that when you do work on an object, you're causing a change in the object's energy. Okay, you're going to cause a change in its energy. And today we're going to talk about how work and energy are related to each other. So let's go back to this simple example, and I kind of like this one after the last couple of days because it's really easy to show. When I apply a light force to this eraser, it moves, eventually it stops. So what I'm doing is I'm pushing on it with a positive amount of force because it's going in that direction. So I'm giving it what kind of work? Positive work. I'm doing positive work to the object. When friction opposes its motion, what do we say? From 6.1, what do we say when friction opposes motion? What is friction doing? What is friction doing if the angle is opposite? Look at your notes if you have to. Joe, go ahead, yeah.
Doesn't it make the angle 180?
Good. Very good, Joe. The angle is 180 when friction does work. What about that 180 did we also say?
So it would be -1.
Yeah, cosine of 180 becomes -1, right? So the work done by friction is generally negative. The work done by friction is negative. The work done by something that helps the object to move is positive work. I need you to consider this idea because it's going to relate to today's lesson where we think about positive energy and negative energy, a gain or a loss. In chemistry, you've used the phrases exothermic and endothermic, right? When it releases or absorbs heat, usually in that case, because therm, heat. But same idea with energy here, we're going to see. So let's take a look at the second slide. Let's jump right into this. So kinetic energy. Kinetic. We talked about kinematic, kinetic. They sound kind of similar, right? The roots are the same. Kinematic and kinetic all have to do with motion. Motion, yes. So we're talking about something that has to do with motion. So if I look at the equation, I have the letter V in there for velocity. It's got to be involved in this because this has to do with motion. Just like work had to do with a force applied over a given distance, those were in the formula. Just like here we have velocity in the formula because the object has to have motion. Well, mass is in the formula too, which is logical, right? If you don't have mass, are you an object, really? No. Physically, you can't exist without mass. So anything that exists, anything that has any energy at all, has to have mass. And that's actually going to go even further if you want to take a look at more modern physics with E equals mc squared, relating energy and mass with waves. And that's what Einstein came up with, the idea where he uses c as the speed of light. We're going to probably get to that towards the end of the year. I cut that out last year, though, to be honest. We never got to that topic. But mass and velocity are both important things to determine the amount of kinetic energy. So when we think about this, an object can have high kinetic energy because of two reasons. It could have a high mass or it could have a high velocity. How many of you watch football on a weekly basis or maybe do a fantasy team or anything like that? So I was watching last week. I love sports. I was never a big football advocate, but I do watch a lot of the Jets. In fantasy football, I've started watching more, but I still don't know players. But I'm a Jets fan, so I hate the Patriots naturally. Sorry, Patriots fans, wherever you are. Are there any Patriots fans in here?
It's only Emily.
It's only Emily? Oh, okay. That's actually good. In the senior class, there are a lot of Patriots fans. In the older class, there are a lot, yeah. I used to always have this last year. I come in on Monday, I needed to hear it every week. So I was watching the Patriots game actually on Sunday night only because the player of the team was on the fantasy team. And they were talking about Gronkowski and whether you like or dislike Gronkowski for his antics and other stuff. He's a phenomenal football player. And they were talking about the fact that he is a double threat. And I'm talking about this because it relates to physics, obviously. I'm just going to talk about it. And in the conversation, here's what they said. Most wide receivers can usually outrun, or they try to outrun, the defensive backs. Most tight ends can linebackers power through linebackers or try to. Gronkowski's kind of a combination of both because he's a really fast runner. So linebackers have trouble covering him because he's really fast, and linebackers aren't as fast. They're usually bigger guys. But at the same time, although he's really fast, he's also very big. So defensive backs have trouble covering him as well. Usually linebackers cover bigger players like tight ends. So as a result, what they'll do is a lot of the time they'll play some sort of a zone or double him, or they'll have like two guys kind of spying him, one that's bigger and one that's faster to compensate for both of those attributes. But then you're down a player that's not covering someone else because you're double teaming someone. And what the announcer was talking about was exactly this. He was talking about Gronkowski's kinetic energy or momentum, either one. They're both functions of mass and velocity. And in a given football game, for someone to get tackled, the object has to have more energy than the other object. That's what it comes down to. If I have more kinetic energy than you and I'm running into you, I will run past you or through you or whatever. If you have more kinetic energy than the person running into you, you will tackle them. So it's all about a balance of energy and momentum, and he's the kind of person who has both of these parameters or variables in his favor.
I was going to say, he has a younger brother. Most people say he's like a better all-around athlete.
Is that right? How much younger? Like, is he not a professional player yet?
I think he is in the NFL. I think he plays fullback.
Okay. So he's supposed to be better than Gronkowski?
I don't know better, but just like a better all-around athlete.
Interesting. I'd have to see. So he's probably got both of these attributes as well. So if you have mass and velocity, you're that double threat. You're the double threat there that we're talking about. All right, let's quickly take a look at the units. These units turn out to be joules. Joules are the same units we talked about for work, and they're the same units we talked about, or we're going to talk about, we didn't talk about it yet, for potential energy. So let's take a look and make sure these units make sense. What are the units of mass? What are the units of mass right away? Mass is? Kilograms. And velocity? Units of velocity?
Meters per second.
1/2, does that have units? No, right? 1/2 is a constant. So those are my units here for mass times velocity squared. I'm literally just taking the formula, right? I don't have to copy down the 1/2. And this becomes, as a result, kilogram times meter squared over second squared. And if I look at this at first, it looks like, oh, this is not really units of joules, but it actually is, and let me show you. Here's why. I can rewrite this as kilograms times meters per second squared, all times meters. I can break up the meters into part here and part here. And this is really a Newton. And a Newton times a meter was what a joule was defined as from work. So if you forgot from work, this is what a Newton is, and that's times a meter. Okay, I can carry the brackets down the whole way to show dimensions, but I was getting lazy. Okay, but that's the reason that this is a joule. This is what it starts with. If you continue down with the units, you'll see that it becomes a Newton times a meter. And a Newton times a meter was what our definition of a joule was when we covered work in section 6.1. All right, let's get into the next thing. Let's take a look at an example. So this is pretty much what I was just talking about, right? With the concept of a football player having either mass or velocity. If you have one of the two and they're pretty high, it means that the value itself of kinetic energy will be rather high. Here we're looking at an example where we have a high mass in the bowling ball. Right? The mass of the bowling ball is 12 kilograms. It's actually it's a rather large bowling ball. It's actually too large. It's like 26 pounds. Have you gone bowling before? Bowling ball is only like 15, 16 pounds usually. Although professionals use heavier ones, not this heavy, so that number's a little bit off. I should make it like 10 really, or maybe 8. Either way, it doesn't matter. The velocity of the ball is 3 meters per second, and we're trying to figure out, you know what a bouncy ball is? Those little like rubber super balls? Okay, with a really low mass of 4.5 grams. We're trying to figure out what velocity should the bouncy ball have to have the same kinetic energy as a bowling ball. The bowling ball has a high mass and pretty low velocity. The bouncy ball is going to have a really low mass, so what should it have? As a result, to have the same energy, what should it have? A really high velocity. So if you've got one or the other, right, if you've got a high velocity or high mass, you'll have a rather high kinetic energy. So here, if we want to balance them, we have to recognize the direct and indirect relationships occurring here. So for the bowling ball, we can list our kinetic energy right away. We're given mass, we're given velocity. So some students in the other section said, let's find kinetic energy for the bowling ball right away. And we can do that. And that's fine, it works. And then we can take that kinetic energy and set it equal to the bouncy ball, which is asking us how fast should it travel so it has the same kinetic energy. So I could find one separately and then set it equal to the second one. Totally okay. But what else could I do algebraically? What have we been doing more of in physics than you do like in math, for example? What can I do to start this problem to maybe help me with a generic solution instead of using numbers? What do you think I could do, Joe?
Well, maybe like first write out the equations you're going to use.
Okay, so I could say the kinetic energy of the first object will be 1/2 mass of the first object times the first object's velocity squared. I like that. And then the second object will be?
K2 times, no, it's equal to 1/2 mass to, and then the I squared.
And I and F are the same here, but 2 is correct, yeah? I say I and F are the same because we're not talking about a change in velocity. We're just trying to find out what the velocity is for this to be true. And we want these to be equal to each other, right? Isn't that what the statement says? The kinetic energy of the small bouncy ball should be equal to the bowling ball if its velocity is great enough. So as a result, we can set these equal to each other instead of actually going through the solution with numbers. Okay, so set these equal. Maybe write yourself a little note. Set the kinetic energies equal. Because of this statement that's circled in yellow. We want them to have the same kinetic energy. So this method is very reasonable. And although we've only just learned about kinetic energy, it's not a very difficult formula to use. So we can simply start by writing it this way. Why do I do this? Why do I do this again? What am I trying to search for? What do I keep calling it? I don't want the exact answer. What do I want?
You're trying to prove that it's the same kinetic energy.
Okay.
So if they're equivalent, then that means the kinetic energy they produce would be the same.
Agreed. But what my question is more, what am I searching for? Joe's right. We're saying that the kinetic energies are the same to start. But what's the goal that we're trying to...
Velocity?
Yeah, we're trying to find the velocity of the second object. But I said never not the exact number. I want a generic solution is the word I've been using. I want a solution in terms of other variables. So on both sides, there's 1/2. Cancel. I can do that because everything on each side is a factor. This is multiplication. If there were addition, every term would need a 1/2. If there was, imagine here, please, imagine a plus sign right here with another term. If that had a 1/2, then you could cancel all 3 1/2s. The minute you have another term on the end, it's got to also have the common factor if you're going to reduce them all. Keep that in mind because we're going to do that later. So at this point, we have the equation without 1/2. Our goal is to find V2. So let's get rid of M2. How do I get rid of M2? I want to get V2 by itself. Fiona, what do I do? Yeah, let's divide. M2's cancel. M2's cancel. So that leaves me with this over here. And that equals V2 squared. God bless you. I want V2 by itself. So obviously, what should I do at the very end, Andre? Take the square root. Okay, recognizing that my answer could be positive or negative depending upon direction. In this case, it won't matter. Okay, because we're looking at kinetic energy. When you square it, it becomes positive energy anyway. It's something good to point out, right? You're squaring velocity. So you're ever going to have a negative kinetic energy? No. It's impossible. If you have motion, you have positive kinetic energy. Maybe jot that one down also, right? If you have any motion, you have to have positive kinetic energy because velocity is always squared. So even if your velocity is negative and you're going that way, you're still squaring it, and as a result, giving me positive kinetic energy. So this is my answer. I just have to plug in at this point, but I need to list stuff. So let's call this the bowling ball because if we're looking for V2, that means that mass 2 must have been the bouncy ball. How do I write M2? I feel like I should rewrite it, right? Something's wrong here. Rick?
Could we 450 kilograms?
The other way. And it's 3 spots, not 2. And the other way. All right? 3 spots, right? Because it's kilo's 1,000. Think 3 zeros and 1,000. It's 3 spots, and you're going from grams. Think about grams. Grams are like paperclip weights. A paperclip itself, I think, weighs like a gram or so. And paper clips are clearly going to be very lightweight, right? So this number has to be really a pretty small number. So it wouldn't make sense to make it 450 kilograms. So those are our values that are given in the problem, and we're looking for V2. So I didn't list the givens in the beginning, so to make sure that we're clear on what they are, they're in that box in the top right. Mass of the bowling ball, velocity of the bowling ball, mass of the bouncy ball, and we are looking for V2. At this point, we're literally just plugging into this equation. Okay, we're literally plugging in. Please remember, although I'm showing you it this way, if you want to plug in numbers early, you absolutely can. If you want to plug in numbers this early, all the way up here, and find the kinetic energy, and then later on use it to find the velocity of the second object, that's totally fine. Okay, it's totally fine. I'm just trying to show you guys new ways to do stuff that I think is a little easier. So what does this become? We have the square root of 12 times 3 squared over 0.0045. And I know it's units of meters per second because it's velocity I'm looking for. I know it's plus or minus, but I'm not going to be concerned too much here just because of the simple fact that, again, it's positive energy, so I don't know, this could be negative, it could be positive direction, I don't know. The ball could be going that way, it could be going that way, that way, that way, that way. It still has positive energy, okay? It doesn't matter the direction of the velocity itself. You have an answer for me, or?
Yeah.
What do you got?
154.9.
154.9?
Yeah.
So clearly a much, much, much greater velocity than the bowling ball because its mass is much, much less. Just compare the masses themselves, right? Look at the masses. By the way, it's not going to be proportional because V was squared. So you can't say, oh, if I divide the masses and get a factor of increase or something, I can then just multiply the velocity and see how much it goes up by. It doesn't work that way because velocity is squared. So don't think that your factor is going to be the same. You know what I mean by factor there? You can see, oh, the mass is like 30 times greater. So the velocity of the other object should be 30 times greater. Not the case. Okay, not the case because of the square. It will be the case when we get to momentum because the formula is very similar to this without the square, actually. So again, just the conclusion I want you to see is that this is a far greater value than the velocity of the bowling ball because the mass of the bouncy ball is so much less than the mass of the bowling ball. You have to compensate for it. It's like a little balancing act. Yes?
What happens if you throw a bowling ball 3 meters per second and a bounce ball that?
Technically speaking, what would happen? The bouncy ball would rebound off of it because of its material property. It's rubber. The bowling ball would probably continue to go. They would have the same energy, theoretically, so they should like hit and stop each other. It wouldn't happen, no, because the materials are actually different. But technically, they should stop.
Maybe they were the same material?
Like if they were two bowling balls, one much smaller with a much smaller mass with the exact same material, they should hit and stop with the same energy, theoretically. But it never actually happens. Because we're going to talk about when objects collide, there's energy lost due to like a deformation if it changes shape. If you dribble a basketball, look at a basketball when you dribble in a high-speed camera, the ball literally compresses every time. Look at a baseball being hit by a bat, the ball actually compresses. A tennis ball is actually a great example. A racquetball is the best. If you've played squash or racquetball, those balls, they compress so much, they become like an ellipse. Like they go from a sphere to an ellipse when they're hit. You don't even see it. The change in shape takes on energy. So this energy is never really balanced. We're going to see that in section 6.3 and 6.4. We're going to talk more about that. But theoretically, they would stop. They're not going to, though. Yeah, good question.
How I saw like this slow-mo video of a golf ball being hit.
Did you see the deformation of it?
Like compressed, like.
It's incredible how much things compress, and you wouldn't actually believe it because their material properties have elasticity, so they regain their original shape. We talked about plasticity, I referred to already, like a plastic bag. Does it go back to its shape if you stretch it? That's plasticity. Elasticity returns to its shape after collisions. And we're going to talk about elastic collisions also. Okay, these are good questions and comments, guys. They're all related. Yeah?
So are they designed for that? So like you don't even notice?
Yeah, for that purpose. That's why inside of a baseball, if you've ever taken the casing off of a baseball, it's like a rubber core. And outside of that, it's all wound up. It's to allow the absorption of the actual compression and expansion. Okay, so we're going to talk now about what's called the work kinetic energy theorem. So you've seen already, and it's very obvious, just based on this simple example, right? I do work to the eraser by pushing it. I do work. I'm giving it kinetic energy. So there's going to be a relationship here between work and kinetic energy, and we're going to show that right now. All I want you guys to do, honestly, is just sit back and watch for a minute. I'm going to do a quick derivation, which I don't always do, but we have the time, so So I want you to see what a derivation is. I'm just going to take a couple formulas and put them together to make a new formula. So we're going to use old kinematic stuff with newer stuff, with energy, to put those two ideas together. We'll start with our definition of work in one dimension. And work was FD cos theta. So we're going to start with that. Now, if we're looking at God bless you. If we're looking at one-dimensional work, it means the force is not applying at an angle. So what's the angle going to be if I'm applying a force in the same direction as motion? 0 degrees. And what was the cosine of 0 degrees? Anyone remember? It was 1. So if I assume that theta is 0 degrees, this next line becomes W equals FD. Because cosine of 0 is 1. The 1 doesn't matter. So I've got W equals FD. Again, by the way, you're not going to be asked to repeat this on like a test or anything. So the very end of it is what you're going to be relied upon, or going to be, oh, geez, you're going to need to know the very end of the problem. If instead I want to take a look and replace force with something, I can remember from Newton's second law, F equals, Chris? MA. So I can replace this and get mad. Then I can change the order here. I remember that with multiplication, the associative property exists. So what I'm going to do is I'm going to rewrite this. And I know it doesn't seem like much, but it is. I'm going to write it like this instead. Okay, the associative property tells me I can group things differently. So I'm just going to change the grouping. That's all I'm doing. So replace F with MA, because F equals MA. That goes in right there. And this is my next line. Now, at this point, I want you to pause. And what we're going to do is we're going to retrace and go back to an old formula. We're going to take a look at this formula. Now, if it's one-dimensional motion, right? Take a look at the eraser, please. One-dimensional motion. If I move this to given displacement, and it's only one-dimensional, the distance is going to be equal. So I'm going to replace x with d. And it seems like not a big deal, but it is. I'm going to replace x with d. And now I can see that in this formula I have AD. Over here I have AD. I can probably combine these two formulas in. So let's solve this formula here, please. Solve this for AD. Solve this formula here on the right for AD. And that sounds kind of weird, but think of this as a variable, what I've just underlined. Get rid of the VI squared, get rid of the 2. Leave AD on the right-hand side, that whole term, AD. So subtracting VI squared from both sides first gives me this. Right, when I want to move something over, a whole term, I just switch the sign. So put a negative sign for the VI squared now. How do I get rid of the 2? By what operation? Division. Cancel my 2's, please, on the right-hand side. And there's AD. For those that are intuitive, maybe you can see already what's happening. Okay, try to take this concept here, plug it in here, and think about what's happening to my equation if you want to get a little ahead, or get a little bit ahead of us, what we're doing here. If I replace AD with VF squared minus VI squared over 2, take a look at the formula itself. What do you recognize here? Anybody pick up on it? Yeah?
Isn't that another one of the formulas on the formula sheet?
It looks like it. Not exact. You need to morph it a little bit. Andre?
I don't know why, but it seems somewhat familiar. It looks like the kinetic energy a little bit.
It's similar to kinetic energy. In kinetic energy, we had mass, we had velocity squared. It was 1/2, and this is divided by 2. So it is related to kinetic energy. Let's go to the next line to prove that. But Andre's on the right track there. Distribute the mass to the numerator. Rewrite this separately. And when I divide by 2, it's the same thing as multiplying by 1/2. So I end up getting pretty much kinetic energy at the end of the problem minus kinetic energy at the beginning of the problem. Final minus initial. When I do final minus initial, what's the symbol we use for that instead? Instead of writing final minus initial, what symbol do I use? Delta. So this is kinetic energy final minus initial, but I'm not going to write that. I'm going to write delta KE. There's the work kinetic energy theorem. All that work we just did, all that work we just did to come up with that last line there, W equals delta KE. Now, this is what's given on your formula sheet, in the box. That's what's given, literally. You're probably never going to use this exactly, but instead you're going to go up 2 lines here and use this formula most likely. Because most problems are going to give you stuff about the mass and velocity, so you're going to probably want to use the formula that involves mass and velocity. So please recognize how to go from what's in the box to 2 lines above it. You should physically be able to write, okay, look up to me so I see what I'm saying. Delta means change, so write that as final minus initial. Replace KE final with this, replace KE initial with this, and you should be able to use that line. Now, what's the definition of work? It was FD cos theta. You could also replace work with FD cos theta. And we're going to see that in the next example, that sometimes you might even want to use this formula. And this is all just the work kinetic energy theorem, just replacing formulas right now. So this is another version of the work kinetic energy theorem at the bottom. All I've done is replaced work with its definition. The definition of work is this right here. That's work. And this is delta KE. So it's useful to recognize that based on what you're given, you may have to use a different form of this formula. If I gave you physically, I said to you, the kinetic energy of an object is 7 joules. A minute later, its kinetic energy is 10 joules. How much work is done? You don't need to use any formula except for this right here. Is that clear why you want to use this formula? You started with 7 joules of kinetic energy. You ended with 10. What's the change in kinetic energy? Physically, what is it?
3 joules.
3 joules. And the change in kinetic energy is defined as the work, right? So if I said to you how much work is done, the answer is just 3 joules. You don't have to use all this stuff here at all. But if I gave you a problem that said, find the force of friction that's exerted on an object as a result of its velocity changing from some value to some value, if its mass is given as something with the distance given, you need to use this formula. Do you see what I'm saying? So you have to recognize that pretty much the last, couple options here can be useful. This one, and this one. Those can all be pretty useful. Depends on what's actually given in the problem. Depends on what is actually given. We could even say FD cos theta equals delta KE, use it that way, which is true, because this is just delta KE. If we're given the change in kinetic energy, we can get that number, maybe it's 7 joules, we plug that right in. You don't have to do any of this work instead. It's just 7 joules of change. And then be able to find out the distance of the force. So it depends on what is given to see which of these you're going to actually use. Okay? I want to do an example to show this, but I wanted to make a point of that you have several options here from one governing equation. You can replace. Remember we did this in the last chapter? F equals ma became Fp minus Ff. And then Ff was replaced with mu Fn. And then Fn was sometimes replaced with mg. Remember all those substitutions we did? That's what's happening here. I'm substituting for work with its definition, if necessary. If I'm looking for F, if I'm looking for D, if I'm looking for something to do with that. Okay, so let's look at this example to see this. Here's an opportunity, second opportunity of the year for extra credit. I gave you one in the last test. Nobody did it in the whole junior class. Remember the elevator ones? Okay, that one's expired, so it's due before the test. So this one will be due before the next test. So you have Thanksgiving break to consider doing it if you want. It's a very easy one. Okay, it's a very easy one. So if you've seen the clip from Risky Business, Tom Cruise comes in the middle of a scene playing the guitar and he slides in on his socks. It's like a famous scene in a movie. So this is pretty much what it is. Have you ever put new socks on and they're nice and slippery and then you get that nice new sock feeling? So I want you to do this at home, okay? Put on socks, or something you can slide on easily. And come running into the room, videotape yourself doing it, in full clothes. Tom Cruise does it in only boxers and a guitar. Please do not do that. I've had people say things like that. Fully clothed, I'm saying it now, it's recorded, fully clothed. Come in to the room, and you have to like kind of slide into the room, but like get a running start and like glide across the floor. Okay? In this example, we're gonna find D, the distance traveled. When you do it at home, you're gonna be able to measure how far you travel. So you're gonna find VI actually, if you do this at home. And you're gonna see where VI comes up in the formula here. So that's basically what's happening. You're coming in, you're running. In this case, the person, whoever it is starting with a velocity of 2 meters per second. They start to slide at 2 meters per second. Eventually, what do they come to? They come to a stop or rest. So the final velocity is going to be 0 here. We want to find out how far you're going to move if the coefficient of friction is given as 0.1. And if you go back to the last slide, you're like, we never had coefficient of friction in our formula anywhere. How is this going to be possible? But think about where coefficient of friction is embedded. Where is that mu symbol embedded? In what formula? In the force of friction. Ff equals mu Fn. So we're probably going to use the force of friction as our force for work. Because work is Fd cos theta. Okay, think about it. I personally am accelerating, and then as soon as I start to slide, the only work being done is friction. The only thing slowing me down is friction. So as a result, when we look at this formula, and I take a look at this here on the left-hand side, I'm going to label F as actually FF, because it's friction that is doing work on me. What angle, Joe? You said it earlier. What angle does friction do work at?
It would be 180 degrees.
180 degrees. So Joe already picked that up from earlier. And cos of 180 is -1. Okay, the cosine of 180 is -1. So my formula is already becoming nice and simplified. Change in kinetic energy is final minus initial. What can I automatically cross off? What can I say goes to 0, Chris? Say again? Be careful. We're not given the mass. You're right. So mass is probably going to drop off later. But before I cancel mass, I'm saying what can I say out of these is going to drop off? Help me out. Yeah, because why?
Because the initial speed is 2 and then it comes to a stop.
Yeah, you come to rest eventually. So let's drop this whole term off. You have no kinetic energy at the end of this problem. Ke final, this whole term is 0. Ke initial is there. Okay, it's still there. So let me copy that down. It's going to be -1/2. Oops, it's a negative. mvi squared. Negative is on both sides, we can see. So what can I do if it's on both sides, obviously? So the negative is gone. Let's get rid of that. What can I replace FF with that Rich said a minute ago? Rich, sorry. I have a friend, Rich. It's Ricky, too. I go back and forth.
0.1 Fn.
Yeah, mu times Fn. Stay with me, please. So I cancel the negatives. That's on both sides. Do that once here. Then replace FF with its definition. I'm doing this because the goal is to figure out the distance traveled. And this problem gives me mu, so I'm probably going to use mu, right? The problem is that I don't have Fn, and I don't have mass in this problem. I've got initial velocity, that's 2, but I don't have mass or Fn. Can somebody give me some piece of information they know that if you're moving horizontally, something occurs? Or there's something specific?
Oh, I was going to say Fn, because you said it's Ng, and then the N would cancel out.
That's exactly it. Very good. And the way we can rationalize or agree with this is if I look at a free body diagram in the vertical direction, normal force is up and gravity is down. That's it. Obviously, friction is acting against your motion, so after you start to slide, there's friction. Fine. But that's not in the vertical direction. So So in the y direction, I know that the normal force acting up is balanced with your weight acting down. So you can replace the normal force with Fg. It's equal to the weight. And Fg, as Katie told us, is m times g. I can show that extra replacement. I'll do it just to be nice. But we have to replace it with mg. And that allows us to cancel out the m's, as Katie mentioned, on both sides. Why was that important? Chris pointed out in the beginning. Chris recognized that m was probably going to cancel out because we weren't given the mass in this problem. This answer is independent of your mass. Independent of your mass. Meaning the mass does not affect the answer. So pause here for a second and take a look at what we've got. If you guys want to do this for extra credit, what are you trying to get? What did I say? What are you going to use your example to measure? Yeah, so how would you get VI by itself? You're not going to do it right now. You don't have to for this problem. But for extra credit, multiply by 2, take the square root. You've got your VI. And you can measure, shoot. Mu is going to be tough to measure, I guess. Let's do this. Change it. Find mu. And I'll explain how you can do it. D you can measure. When you take the video literally, if you want to, you can put a tape measure on the ground or have your brother or sister mark off where you start sliding to where you stop sliding. Measure it. You can figure out how to measure D on your own. That's easy. To measure V, you could use the video vernier app. And you could literally use that to record. Right? And then you could use, remember how you put the dot for every part of the lab? And then you were able to look at the graphs and you were able to get the initial velocity and stuff. So figure out a way to measure the initial velocity itself using the video vernier app. So if you don't have it, either download it or do it with a partner so at least so you have the video. But use the video tracking thing where you put a dot in the middle. Use this as your center of mass when you're sliding. So put the dot here every step along the way. And then in the very beginning, you'll get the plots and you'll get your data tables and you'll have your initial velocity. Just like you got the initial velocity when you tossed it up, was when you released it. This will be when you just start to slide. That's the velocity you want to get. So get the velocity, get the distance by measuring the velocity from your data collection device. Okay. Solve for mu. Okay. Find the mu for extra credit. This turns out to be for D. We're looking for D here, just so you're aware. The answer looks like this. Okay, that's what it will look like algebraically. I'll put the VI squared up top, the mu G down below. So this is 6-2. You don't have actual homework due tomorrow yet, but you can get started on anything with kinetic energy and the word kinetic energy theorem tonight. Don't start with potential energy until we go over that tomorrow, please.
The extra credit, can my sister do it since I can't?
Yep, as long as you videotape it and then explain. You have to explain the physics behind it happening now. All right, so this next idea here, we started 6-1 with work, and work causes some sort of a change in energy we've been seeing, because when I do work on an object, it causes it to move. Motion implies that it has kinetic energy. Now we're going to start, we're on the next slide. Sorry, it's not showing up there. Okay, so go to this next slide with potential energy. Now we're going to start with the concept of the association of energy due to a state of being, not motion itself. You pull back on a rubber band. When you let go, why is it able to launch? Why can it physically get launched across the room? Why is it allowed?
It's like storing up energy, and then when you release it, all that energy is
Converted to what?
to kinetic.
Kinetic, good. So we're kind of already looking into the idea of conservation of energy. We can store energy, and then that energy can be transferred into potential energy or kinetic energy. Give me a sec. Let me try to maybe hit stop mirroring and redo it. Is this frozen?
It just disconnected.
I disconnected?
Yeah.
All right. So somebody's already being used, it says now. Any Seinfeld fans in the room? Yeah?
I
Love
know
Seinfeld.
Jerry's daughter.
No, you don't.
My friend is dating his daughter.
Really?
Yeah.
Jerry Seinfeld's daughter.
Yeah, her name's Sasha. She doesn't chase it.
So does that mean you would technically know Jerry Seinfeld if you wanted to?
I begged my friend come.
Meet him?
With a lot of money.
My dad would love to meet Jerry Seinfeld. He's a huge Seinfeld fan. It's just like really delayed. Like I've already gone past this. Okay, so no big deal. So if we store energy somehow, for example, by pulling back on a rubber band, that kind of energy we're going to see in a minute. We're going to call it elastic energy, but it's still a type of potential because you're changing the shape of something to give it energy. Look at your definition. The energy associated with an object because of its position, shape, or condition. So the shape is being changed, which is storing energy. The condition, how about that one? Condition. Think about some sort of like a nuclear bomb or anything that has energy because of its condition. Right now, it's not giving off energy, but it can give off energy. Think about a grenade. The actual fragments of shrapnel that explode from a grenade, each one of those has energy. Where did it come from? It came from somewhere. It had some sort of internal stored energy. That's its condition that we're referring to. The first part, though, I'm underlining, but you can't really, it's not going to show up, is position. The position of an object gives it energy. Why does that happen? Because the position has to do with the second part here called the gravitational potential energy. And that's what we're going to really focus on in this section. So I look at this paper clip, and I compare it to whatever this is. It's metal rod. If I were to drop them, I'm not going to. If I were to drop this, it'd probably make a really loud noise, right? If I drop this, it's going to make a loud noise. Doesn't have much what? Doesn't have much.
Potential energy.
Yeah, potential energy, because this is really massive, and this is not very massive. And look at potential energy. What is it a function of? Mass is one of the things it's a function of. What else is it a function of? mgy. What else?
It's like how high you hold the object.
Yeah, how high above the ground or above what you call the ground. You hold it. So watch, ready? I drop the paperclip to the table. So the table is the ground technically, right? Because it stopped there. I drop the paperclip over here from the same initial height, but now the ground is actually the ground. Now the floor is the ground. So as a result, it undergoes a higher change in height, a higher y value. So by holding it here, it has a lot of potential energy compared to the floor. Compared to the table, it doesn't have as much potential energy, right? Compared to my hand, not very much potential energy at all. And now, no potential energy. I let go and it's just stationary. So the actual reference frame depends on what you call the floor. Do you see what I'm saying? So if I'm holding it here, this y value is now 6 feet. I'm not 6 feet, but this might be. If I hold it here, though, it's probably only about 4 feet, maybe 3.5 feet. So the potential energy is a function of the height y. Mass and y, those two things affect it. Units? Do the units make sense here? Write your units out individually. What are the units of mass? We can do this. We've done it before. You guys can definitely do it on your own at this point. Just literally list your units. Is it responding? No, of course not. The units of mass are, write it down as we go. This is really not working today?